Well, welcome back, everybody. Hope everybody can hear me. I'm smack in the middle of Tucumcari, New Mexico at a park. And this is cool. I don't do this more often. I like this. Nice and breezy. So hope everyone's doing okay. I had a question email. I just was able to check my email. There's a question. I think, Natasha, you had that. We can go over those three problems right after this chapter. What I want to do is finish chapter 12 to get you ready for the next exam. And then we can go over those three questions you had and any other questions that you may have. Now I'm keeping an eye on my battery. I'm about three-quarter battery, so I'm doing okay. I'm running off a hotspot. Shouldn't be a problem, but if we get disconnected, just hang loose. I'll reboot something and get back online. Okay. All right. Any quick questions right now need to be addressed before we begin? Okay. Hope you enjoy the background. It's a nice little park out here. Yeah. All right. Chapter 10. This bear with me. Excuse me, 12. What am I saying? Okay. So the exam obviously will be 10, 11, and 12 for this weekend. It will open again on Friday morning, and it'll be available Friday and Saturday until 11 p.m. Okay. And I'll stay close to my cell phone in case there's any questions that need to be addressed. So I will be back when I'm done here. I'll be back on the road, but I'm gonna stop probably in Liberal, Kansas, and get a place there. So I'll check my emails in and then be in the Kansas City area the following day. So anyway, so bear with me so that I don't get back to you right away. All right, the concept, the mole concept. This concept can be challenging at times. However, the thing about the mole, plain and simple, is this. A mole is simply a number, okay? That's all it is, a number. You know, we're all familiar with another, make sure, it's tough to see my screen here a little bit. So, you know, we all know that in a dozen, right, there are 12 units of whatever you want to measure, okay? So the mole is very similar. It's nothing but a number. It just happens to be a humongous, big number. So 1 mole, with respect to what its value is 6.02 times 10 to the 23rd units. And I say units because it doesn't have to be chemical. It could be anything. It could be bananas if you want. It could be donuts. But we happen to use it in chemistry. It happens to be maybe atoms. It could be ions, you know, so on and so forth. So, you know, we grasp the concept of a dozen. If I say to you, you know, a dozen eggs, actually, you know, there's 12 eggs. And when we talk about a mole, well, we got a number. It just happens to be a big number. We call it actually the chemist dozen, which is 6.02 times 10 to the 23rd. Now, to give you an idea how big that number is, take that decimal point, move it over to the right 23 times. So guess what? Remember that scientific notation we were learning way back when? Well, here we are. We're going to need it again. So refresh your memory on how you inputted scientific notation in your calculator, okay? Because we'll be doing calculations, okay? Now, using this big number. Since I'm having a little bit of a challenge at seeing the screen because it's kind of bright back here and I got my screen lit up as as bright as I can. If you have a question, feel free to, unmute yourself and ask the question, because I may miss it with respect to the chat part. Okay, so here's a picture of Avogadro. Kind of crazy looking guy here. All right, Avogadro, that number, we use a symbol, the letter capital N and then subscript capital A for Avogadro's number, which is 1 mole, okay? Which is equal to 6.02 times 10 to the 23rd. It just happens to be a very large, super large number, okay? To give an idea of how big this number is, here I've put some of the units we use to describe, the bigness of numbers, if you will. For example, as you know, a billion has 9 zeros, a trillion has 12 zeros, okay? A 6 trillion is 21 zeros. So Avogadro's number is 602 6 trillion. Now, to put it in perspective, if you were able to count, if you counted at 1 number per second, that's my frequency, 1, 2, 3, 4, so on and so forth. To count at that rate of 1 number per second at that frequency, it would take you about 19 quadrillion years to get to the end of the number. Pretty hefty number, okay? But obviously not as hefty as this other ones on here I gave you. They're like a Googleplex is a very big, humongous number. So that kind of puts it in perspective as to how big this number that we're dealing with, okay? Now, as we stated, another perspective, if you had a mole of salt balls, if you're familiar with a salt ball, not quite as, a little bit bigger than a baseball, okay? Maybe 4 or 5 inches in diameter. A salt ball, if we had a mole of salt balls, you would have enough salt balls to be the size of the Earth. Okay, so they're pretty hefty. Now, on the periodic table, you may have wondered, do those numbers, we talked about the atomic weight, okay? I may have briefly mentioned it. I don't recall if I did or I did not, but let me tell you now. Those numbers the atomic weights have units, okay? Obviously the atomic weights here, for example, carbon sitting here, we see the number here, 12.01. We discussed about why that number is decimal number and so forth, okay? But notice there's no units. So I'm telling you now, atomic weights have the units of grams per mole, okay? Grams per mole. So if you were to take carbon and you go out to the lab and you weigh out 12.01 grams, guess what? You're going to have 1 mole of carbon atoms. If I go and I weigh out 14.0 grams of nitrogen, monatomic nitrogen, if that was feasible, it would be kind of difficult, but let's assume that you can. And you weigh out 14.01 grams of nitrogen, monatomic nitrogen, you would have 1 mole of nitrogen atoms. And the same is true for oxygen, okay? Now, let's say we go to silver, okay? You take silver. Now, let me back up. Notice I said monatomic for nitrogen, right? Because we know nitrogen's diatomic. So the atomic weight, the molar mass we call it molar mass for nitrogen will be twice that. Okay, keep that in mind, all right? And that'll be true for all the diatomic elements. So if you go out, let's go back to silver. Go out to the balance, you weigh out 107.87 grams of silver. Guess what? You have 1 mole of atoms of silver. And in each example that I just did, I would have 6.02 times 10 to the 23rd units, atoms, or whatever I measured. If I get 1 mole bananas, I have 6.02 times 10 to the 23rd bananas. A big number, right? Now you say, well, these numbers get bigger. Well, of course, obviously, think about it. As we increase the element size, we increase the number we increase the number of protons and neutrons. Of course, their weight gets bigger. It's analogous to eggs. If I said to you, which one, who's going to weigh more? 1 dozen small eggs or 1 dozen large eggs? Obviously, 1 dozen large eggs, right? Because it's bigger. But in both cases, if I have a dozen small eggs or a dozen large eggs, guess what? I still got 12 of each, right? Okay, they're going to weigh differently because of the size, just like all the elements are going to weigh differently. The fact that the units are grams per mole, refresh your memory about this, the ratios I've always emphasized, that you can take that ratio of grams per mole and write it as either grams per mole or moles over grams. And that will help us when we start to do calculations, okay, where we are converting from grams and we need to get to moles, or when we have moles and we need to get to grams. Just like analogous to the conversion factors we did, where we had, 1 inch was equal to 2.45 centimeters. That was a ratio. And depending on the question, we either set centimeters in the numerator or we inverted it. Same as here. Same is true here. Okay. All right. Let's go back to the mole. And so, if you go to the periodic table and the question says, all right, how many grams does 1 mole of, iron weigh? Well, you don't have to calculate anything, right? All you got to do is go to the periodic table. Go to the periodic table, look for iron, which is right there, okay? And if I weigh out 55.85 grams of iron, I have 1 mole. Alternatively, someone could say, well, how many grams does 1 mole of nickel weigh? Well, that would be 58.62 grams. So with that information, you can extrapolate, I hope. If I'm talking about 1 mole, well, what's the obvious thing? What would 2 moles of nickel weigh? What do you think 2 moles of nickel will weigh? Of nickel. What do you guys think? What do you think? Wouldn't it be twice 58.69 times 2? Because if 1 mole weighs 58.69 grams, well, 2 moles is obviously twice that. And 3 moles would be 3 times that, right? All right. And a lot of times we are, we're talking about nice whole numbers here, but the majority of the time when we do calculations, we're not dealing with nice whole numbers. We're dealing with, 1/10 of a mole, 1/2 a mole. Now you might be challenged with what I just stated here. Okay, but let me put it to you this way. Let's say you have 1 dozen small eggs and they weigh 100 grams. Okay. All right. So if you had 200 grams of small eggs, how many dozen would you have? Could you calculate that? Everyone want to take a guess? If I had 1 dozen small eggs and each weighed 100 grams, that dozen weighed 100 grams. If I had 200 grams of small eggs, how many dozen would I have?
24.
Exactly. You have 24 or 2 dozen. Exactly. Okay. And here we grasp the concept with the eggs. We're going to do the same thing with the mole. It just sometimes it gets challenging because that number just happens to be much, much, much greater than 12. But the same concept is set up. Okay. Now I could take that ratio and let me do it this way. And I said to you, okay, 1 dozen small eggs equals 100 grams, right? And the question was, oh, somebody need to come in. If I said, if I have 200 grams of small eggs, right? How many dozen would I have? Okay, well, let's set up the problem like we do before. We write down what we have. We got 200 grams of small eggs. I just call them SE. I got my conversion factor up here, right? Which is this guy. And I want grams to disappear. So I'm going to put 100 grams down in the bottom, right? Because I want that to cancel. All right. And I got 1 dozen on top. And so there you go. You set up the problem. Isn't that reminiscent of the conversion factors we did? We write down what we have. We use a conversion factor. We set that conversion factor in a manner so that the units cancel out properly, and then we just do the math. And so in this scenario, we've got 2 dozen eggs, small eggs, if I have 200 grams, okay? And I can substitute this information with Avogadro's number, okay? Or I can substitute this ratio with any of the elements as far as their atomic weight. You set it up in that manner. Okay, we'll go through some examples to refresh your memory how we did that. All right, so as I stated, the mole is nothing more but an entity, a unit, and it could be anything. Of course, like I said, I exaggerate and say bananas and oranges, which you can, but since we're dealing with chemistry, we talk about atoms, we talk about ions, you know, we're talking about molecules or formula units, like the whole formula. You can have sodium chloride, aluminum oxide, that number in front, that coefficient is going to tell us how many moles we have, okay? That's what that coefficient is going to tell us. Now, if you're asked, well, how many grams of 1 mole in carbon, gold, and sodium, go directly to your periodic table and just read the atomic weight. Now, the correction here is this. The question is how many grams, and this is, so erase the mole part. It's not right. It's a typo there. Okay, the question is how many grams in 1 mole? Well, in 1 mole, each one weighs 12.01 grams per mole. So moles cancel out. So 12.01 grams is 1 mole. 196.97 grams is 1 mole, and 22.99 grams for sodium. And all these 3 examples have exactly 6.02 times 10 to the 23rd atoms or units of what you're looking for. Okay. All right. Now, when we talk about the atoms themselves, the elements, we're talking about atomic weight. So carbon has the atomic weight of 12.01, okay, etc. When we're talking about the monatomic, the single element. But when we start making compounds and formulas, we use the term molar mass, because the molar mass is the sum of the atomic weights of all the atoms involved in the formula. Okay, so we basically just add up all the mass, all the atomic weights for every element, and that total amount represents what we call the molar mass. Okay, so in this example, they want to know, what is the molar mass of barium hydroxide? Well, before we can do anything, we got to write the formula. And to write the formula like we've been doing, the first thing to do is you got to write it in ionic form. Okay, we're dealing with this compound here, which is ionic compound. So we know that barium has the formula Ba. Oh, hold on. Okay, and so we know barium has a +2. Okay, a +2 ionic charge or oxidation number because it's a group 2 element metal. It can lose 2 electrons. Hydroxide is the polyatomic ion. Okay, if you go to the polyatomic ion table, you'll find that each one has a -1 charge. So I need 2 hydroxides to cancel out the 1 plus 2 from the barium. So our formula is BA parentheses, okay, and then subscript 2, okay, subscript 2. All right, so that's our formula. Now we identify how many elements of each we have. So we got 1 barium, okay, we have 2 oxygens and 2 hydrogens, okay. So we identify all the elements. Once we identify that, we go and look up the atomic weights for each of the elements and multiply it by the number of atoms that are involved in that are in the formula. Okay, and so with that being the case, there's a formula. Barium has an atomic weight of 137.33. That's from the periodic table. Oxygen, there's 2 of them. Okay, 2 oxygens. This is the 1 barium. Okay, this is the 2 oxygens because each oxygen has 16. And then the 2 hydrogens. Each one has 1.01. Tally it up. The molar mass for barium hydroxide is 171.35 grams per mole. Okay, so again, put in perspective, if you go to the lab and you weigh out 171.35 grams of barium hydroxide, you have 1 mole. Okay, and if you double that weight, guess what? You got 2 moles, right? On the other end, let's go the opposite direction. If I take half of 171.35, I got half a mole, 0.5. All right. So here is this ratio that I'm going to utilize depending on the question that I will be asked. Okay, and this is for barium hydroxide. So I would write it either with grams in the numerator or invert it with grams in the denominator. Okay, over 1 mole. And which one I use depends on the question I'm asked. If I'm given X grams of something and to calculate moles, well, obviously I'm going to use the bottom one here because I want my grams to cancel. If I'm given X moles of barium hydroxide, then I'm going to use the top one because I want moles to cancel to give me grams. You see how that works? All right. Okay. Okay. Now, with respect to Avogadro's number, 6.02 times 10 to the 23rd, guess what? That's also a ratio. It is 6.02 times 10 to the 23rd atoms, units, molecules, whatever, per mole. That then I can write either as I do here on the left or as I do on the right. And here, the question is, how many calcium atoms are in 0.25 moles of calcium? Okay, so give us some thought. 0.25, if you think ahead mathematically, that's 1/4 of a mole, right? Think about it. That's 1/4 of a mole, but let's work it through. So like any of the other problems we did before, we write down what we're given. Moles of calcium, okay? We're gonna have a conversion factor, and what are we looking for? We wanna know how many atoms. We wanna know how many calcium atoms. So I write down the units that I'm looking for because I wanna make sure that that's the units I'm gonna end up with. So I get a conversion factor here. Moles obviously goes in the denominator because I want that to cancel. And then atoms, in this case, it's atoms, but it could be bananas, you know. So we want Avogadro's number, 6.02 times 10 to the 23rd in the numerator over 1 mole. So unit-wise, everything looks good. I'm ending up with atoms, which is perfect. Now it's up to you to plug it into the calculator. Remember to type in 6.02. One of the 3 buttons, either double E button or EXP button, or the button that had a X10 to the X power button, one of those 3, and then type in the exponent, okay? And then just do the math like you normally would do. And you get your answer. All right, so if you do that, your answer should be right there. Quarter of a mole, almost a quarter of a mole, a quarter of Avogadro's number, 1.51 times 10 to the 23rd calcium atoms. Now, when it comes to sig figs, the mole, 0.25 moles, that comes from a measurement, okay? So if you're given the problem grams or moles, if you're given the problem, then that comes from measurement. So that could be a factor in your sig figs. But Avogadro's number is a whole number. And so being an exact number, that would not be a factor as far as your sig figs, okay? Just like a dozen, 12 per dozen, 12 is an exact number. All right, now you're being asked to calculate the moles of 3.75 times 10 to the 27 molecules of oxygen gas, okay? All right, so let me bear with me for a second. There we go. All right, so as always, write down what we're given, 3.75 times 10 to the 27 molecules, okay, of O2. Obviously, we need a conversion factor. And what are we looking for? We're looking for moles. So we need to know moles of O2, okay? And so that tells me how to set up my conversion factor, how to set up Avogadro's. Obviously, notice Avogadro's number can be molecules, atoms, as I stated before. So 6.02 times 10 to the 23rd goes in the bottom. And that'd be molecules. That's going to cancel. Then we got on top 1 mole. Okay, 1 mole. And so now, check my units, everything looks good. Bam, plug it in the calculator, and you're good to go. Excuse the noise in the background. Looks like I'm being close to a fairly busy street. So, all right, so there you go. 6,230 moles. All right, so you have 3.75 times 10 to the 27 molecules of oxygen. I have 6,230 moles. All right. Now, in these examples, what we're going to do, we're going to do calculations where we're going to take grams to moles, okay? But being able to go to grams to moles, then the converse, we need to learn to do that too, going from moles to grams, right? So in this case, remember I talked about the molar mass has the units of grams per mole. That means that we're going to set that molar mass either grams in the numerator or grams in the denominator. And how we set it up depends on the question, okay? So question number 1, how many grams is 1.667 moles of oxygen, okay? Okay, so oxygen gas. So this is where you gotta, we're gonna start tying things together. Okay, it didn't say oxygen atom, it said oxygen gas. And you should know, hopefully, by now that oxygen gas is diatomic, okay? Being diatomic, its molar mass, MM, will be 32.00 grams per mole. Okay, because each one is 16. You can look that up in the periodic table. And we have 2 of them. So therefore, the molar mass for oxygen gas is 32.00 grams per mole. Okay. We write down what we're given, 1.67 moles of O2. Obviously, we're going to have a conversion factor here. we're looking for grams, final units. So that's what I'm looking for, units. So that means that grams will be up in the numerator and obviously moles will be in the denominator. Okay, so that is 1 and that's 32 on top. Okay. And check my units. I'm making sure I set this up properly. My units cancel. I'm leaving, I will have units of grams, which is what I need. And I'm good to go. So now it's a matter of plugging it into the calculator and getting your numbers. And you should end up with 53, it's hard to read here, 53.34 grams of oxygen. Okay. So if I have 1.667 moles of oxygen, okay, which is going to be a number a little bit greater. Think about that, a little bit greater than 6.02 times 10 to the 23rd, because 1 is 6.02 times 10 to the 23rd. 0.6 is a little bit over half, so I'm going to have a lot of molecules, okay? And then that would represent 53 grams, 53.34 grams of oxygen. Okay. How many moles is 45 grams of silver? Okay, so now we need the atomic weight. Again, I say atomic weight. Why? Because we're dealing with just the element itself. Molar mass, we're dealing with a molecule, a compound that has more than one element involved. Okay. All right, so here we write down what we're given, 45 grams of silver. Its atomic weight is 107.87 grams per mole. I write it with grams in the denominator because I'm looking for final units of moles, okay? Final units of moles, and the way I set it up here, my grams cancel out, leaving me with units of moles, which is what the question asked for. And now you just plug it in. Okay. All right. And again, when you do the calculations, look at the number. Does it look reasonable? Okay, because if you got 45 grams, and the atomic weight of silver is 107. Roughly half of that, about 50 some, would be half a gram. Half a mole, I should say. And you're less than that, so your number is 0.4 moles. That number is very reasonable. And if you would have done the math and inadvertently inverted it, that number would just hopefully wouldn't make sense. Okay, if you took 107, multiply it by 45, it just wouldn't make sense because you're starting with much, much less than the atomic weight, the molar mass of silver. And I hope that part makes sense. And the whole point is looking at your answers to see does that make sense? Okay. Is it reasonable? All right, here we are asking how many grams is 0.0554 moles of water. Well, we got water here. I'm hoping that you know the formula for water, which would be H2O, right? Now we need the molar mass. So we got 16.00 for the oxygen. And then we got that 1.01 for each hydrogen. So that'll be 2.02 for the hydrogen. So we have 18.02 grams per mole. And that is the molar mass for water, okay? 18 grams. Imagine this. You have 18 grams of water, 18.02 grams of water. You have 1 mole, 6.02 times 10 to the 23rd molecules of water, okay? Now take that and think about all the water on Earth. Heck, just think about the water in your body. Calculate that in the ballpark, I don't know, maybe, I don't know what percentage, but think about all the water in the ocean, tons of water, and then calculate the number of moles. And the number of molecules of water is astronomical. That's just, here on Earth. Okay, so let's write the problem like like we've been doing, write down what we know, what we're given. We got 0.0554 moles of water. Okay. We have our factor here. I'm going to move this down a little bit, right in that space. And we're looking for grams of water. Okay. So that means that obviously we start with moles. Moles are going to be the denominator, grams in the numerator. Okay, so we got 18.02 divided by 1 mole. All right. And check the units. Units, moles cancel, leaving me with grams. And do the math. You should end up with almost 1 gram, 0.998 grams of water correspond to 0.055 moles of water. Okay, 1 gram of water. All right. We got one more. Okay, in this case, you're asking you how many grams is 4.75 times 10 to the 16 atoms of potassium. All right, so I have atoms of potassium. I want to convert to how many grams? Well, here's the thing about these calculations. The concept of the mole is extremely important. Why is this? Because to get from bananas to oranges, so to speak, I have to go through a center unit that is both have in common, and that is moles. Okay, I cannot go directly from grams to grams. I have to pass through moles to get me from grams of A and correlate that to grams of B. I can't do it directly. I have to go through moles, or even through atoms. I have atoms of A, and I want to get to grams of A. I got to go through moles. So moles is the central unit that we have to grasp the concept of, okay? Because that's going to allow us to go from point A to point B. And so as we do, is the first unit, we got 2 units here. We write down the atoms, obviously, 4.75 times 10 to the 16 atoms of potassium. Our second conversion factor is Avogadro's number, okay? With moles in the numerator, because 6.02 times 10 to the 23rd atoms will be in the denominator, and that will cancel out the atoms, okay, to give me moles of potassium. You see that first one, this first unit here got me into moles, okay? Once I got that, now I can go directly into grams based on the molar mass or the atomic weight of potassium. But again, to convert the units, let me write out the units. I got atoms to begin with. Okay, I got atoms here in mole right here. And then at the end, I have grams and moles. Okay, so notice how I go from atoms to atoms cancel out. Here's my moles and my moles, but I needed to get through moles to get from atoms to grams. Okay, and that's our central factor. Notice how small amount of potassium that is. 3.09 times 10 to the negative 6 grams of potassium, okay, represent 4.75 times 10 to the 16 atoms. That is a lot of atoms, but the quantity is so tiny. In fact, most balances, at least most balances in the lab could not weigh that amount. We can do, most balances are good through up to 4 decimal places. This is going to be a little bit challenging to weigh that amount. All right, so that's our conversion from grams to moles. Now, to go from moles to grams is just the opposite. Now, the big takeaway here is this: if you look at the mathematical functions that you did here, notice something. If you start with moles and you want grams, you multiply by the molar mass or atomic weight. Okay? If you start with grams and you want moles, guess what? You divide. So you multiply if you want grams, starting with moles, and you divide if you want moles, starting with grams. Okay. All right. This brings us to the molar volume. Now, earlier in the beginning, we were talking about the physical properties about gases, and it said gases just took the volume of their container, which was a true statement. But we're gonna elaborate on that concept and now give you that under certain conditions, okay, very specific conditions, gases will occupy a set volume, okay? All right, under what we call STP, let me go to here. STP is the following. At 0 degrees Celsius and 1 atmosphere, recall when we talk about pressure, 1 atmosphere, this is where I'm at right now, where we're at generally about 1 atmosphere, and 0 degrees, which is a little bit cold, under those conditions only, the relationship is as follows, that any gas will occupy a volume of 22.4 liters. Okay? Only and only if you are at 0 degrees and in 1 atmosphere. And what that does for us is the following. Now we have, guess what? Another factor that we can utilize in our calculations. We have a new ratio to in our back pocket here to do calculations. It says that 22.4 liters per mole. Okay, that a gas at 0 degrees, 1 atmosphere, and you got 1 mole of that gas, it would occupy a volume of 22.4 liters. And notice here we got different gases, hydrogen down to methane. We got a mole of each one, right? That means that we have exactly 1 Avogadro's number of each one, 6.02 times 1/23. Obviously, the molar mass is different because each one has a different weight. Hydrogen weighs the least and fluorine, okay? But the other thing they all have in common at 0 degrees and STP, that they all occupy a volume of 22.4 liters. And we can utilize that concept to do some calculations. So we now think about this, we can go from moles to volume or vice versa. We can go from atoms of molecules or molecules of whatever gas, get it to moles and get it to a volume, okay? If we're at STP. And that's important because if you're ever given a problem to do, asking to do this calculation, if they do not mention STP, either saying STP, standard temperature, pressure, or actually writing down giving you 0 degrees or an atmosphere, then you can't do the calculations. It's not, it wouldn't be a true statement. You couldn't do that calculation unless you're under those conditions, okay? All right, so that being said, you have that ratio now that you can, like all the ratios we've been dealing with, I can write with liters in the numerator or liters in the denominator. Which one we use depends on the question. All right, so we have here, what is the volume of 1.25 moles of argon gas at STP? Okay, so like any other, 2 things to note this. First of all, they're asking you for the volume. Okay, that's what we're looking for. We are at STP, okay, and we're talking about a gas, okay. That being the case, I can use the relationship of 2.4 liters per 1 mole. I can use that if I need it. So we write down what we're given, 1.25 moles of argon gas. Okay, we're going to have a conversion factor here. We're looking for volume, which would be liters of argon gas. Okay, and so we got moles in the denominator because we want that to cancel, and we got liters on top. So 22.4. Okay, so check the units, everything looks good, plug in the number, and you should end up with 28.0 liters. Okay. Now, 22.4 liters is not an exact number. It is a measurement. So that could be a factor in your sig fig. So keep that in mind. Even though it's a conversion factor, it is still a measurement. So, and then again, ask yourself the question, does that make sense? Well, yeah, because you're about 1.25 moles. So obviously you're going to be more than 22.4 liters, but much less than say 30 some, because you're about 1.25. And that number 28 makes sense here. All right. Okay. Great. Next one says, how many moles? If we have 30.4 liters of O2, we're still at SDP. They want to know how many moles of gas, oxygen gas, are we dealing with? Moles of O2. All right, so liters go down here, moles go on top. We got 22.4 in the denominator, 1 on top. Our liters cancel. Column can set up properly. Okay, and so we can then plug that number in, and you should get 1.34 moles. If you have 30.4 liters of oxygen gas, it should be 1.34 moles. Okay. And we use this if we're out in the lab doing stuff, you're under these conditions, and a lot of times when you're dealing with gases, you really can't weigh them. So but you can deal with volume. You can use flow meters to figure out how much volume of gas you're going to use or transfer to a container. And if you're at SDP, you can take that volume and convert that to moles, because you're going to need to know how many moles you have when you're running reactions. Okay. All right. Now here we have the chlorine gas. Okay. They're asking you, what is the mass? If I have 4.5 liters of chlorine gas at SDP, how much does it weigh? Okay. Now the fact that they're asking you for mass should signal to you and say, okay, I need the molar mass / atomic weight. Okay. Also recognize that chlorine gas is diatomic. So we're dealing with Cl2. Okay. We're at SDP, so we can use a 22.4 liter per mole relationship. Okay. And we need the molar mass of chlorine. Okay. And we're good to go. So it's a matter now of getting all that information, setting it up as follows, because the first one is 4.5 liters. We need to convert that to moles. Just like I stated before, any of these calculations, I cannot go from liters directly into mass at SDP here. I need to go to moles, and the common factor is moles for all these calculations. So the first factor converts the liters of chlorine gas to moles of chlorine gas. And then finally, the last factor converts it into a mass, okay, into a weight. So 4.5 liters of chlorine gas would weigh 14.2 grams. All right. So this flow chart would summarize everything. Notice the key is moles. And we're going to have another flow chart when we do more calculations, more extensive flow chart that incorporates other aspects of calculations. But in both sets of flow charts, the center point is moles. I cannot go from A to B without moles, okay? I need to learn, if I start with grams of whatever entity, I need to learn how to determine the molar mass. Most of the time, if it's on just the atom itself, I just find its atomic weight and good to go. If it's not, if it's a compound, then I need to write the right formula that we've been doing, breaking it up into ions, okay? Or deciphering if it's in a covalent compound, deciphering what the formula is based on the name. And then once we know the formula, we tally up all the atoms involved in the formula. Okay, that gives us the molar mass in units of grams per mole. Okay, now from there we can go into moles. And once we're in the moles, starting from grams, we can go any direction here. We can calculate atoms, ions, molecules, whatever is needed. Or if we are at STP, we can calculate the volume of that if it's a gas and at STP. Okay, so. But before we can do anything, we got to go through moles. So the concept of moles is very, very important. We'll be using it quite extensively. All right. So, for example, how many grams does 17.35 liters of, bear with me 1 second. Okay, I'm back. Okay, so two parts of this question. First part says, how many grams does 17.35 liters of neon gas mass? How much does it weigh? Is the question being answered? At STP, and that's very important. STP, because now we can use the molar volume relationship. Then it's asking you, well, how many atoms does this correspond to? Okay, so let's do the first one. Well, we write down what we're given. I also gave you, I gave you the answer, but the point here was the units I'm looking for, okay? Because that process, that technique of doing this helps us set up the problem properly and making sure our units cancel out. So the first unit, first conversion factor, gets rid of the liters. Okay? It converts that liter of gas into moles. Okay, into moles. So we have liters canceling out, giving us moles. And then the second factor, because we're needing grams, we need either the atomic mass or the molar mass. In this case, this is neon gas, so just the atomic weight. We looked this up in the periodic table. It has an atomic mass of 20.18 grams. We set it up with moles in the denominator and grams in the numerator because we're looking for grams. So check our units. Now you do the math. And so what this tells us is that 17.35 liters of neon gas at 0 degrees and at 1 atmosphere has a mass of 15.6 grams. Okay. Notice there's 3 sig figs here. Okay. 17.35 has 4 sig figs. But like I stated, that conversion factor, that relationship of 22.4 liters, that is a measurement. So it could play a factor in sig figs. And in this example, it does. The answer should have no more than 3 sig figs. Okay. All right. Now, second part was how many atoms we need. Well, we begin again and write down the units we're given, write down the units we're looking for, and there's the answer. So we put in, again, we're in liters, so we're at STP, we need to convert that to moles. Okay, once we do that, since we're being asked to calculate the number of atoms, then we bring in Avogadro's number, and it will tell you how many atoms of neon gas are involved here. Check my units, everything's canceling out properly. I end up with units of atoms. Plug in the number in your calculator and you're good to go. So 17.35 liters corresponds to not only 15.6 grams of neon, but it corresponds to 4.6 times 10 to the 23rd atoms of neon, okay, at STP. Okay. All right. Any questions about this? Okay, notice we set up multiple units. Eventually, we're going to be doing, when we do calculations, we're going to have at least 3 conversion factors to get us to point A to point B. Okay. All right. Now, if you recall, we had talked about density a while back. Okay. Density was another ratio. And this ratio had the units of mass over volume. Okay, so if you have the mass, you have the volume, you can calculate the density. But if you're dealing with a gas and you are STP, guess what? You can calculate its density without even having to measure it. Okay, you're right. So here to ask you to calculate the density of ammonia gas. Well, we need the molar mass of ammonia. Right? And we know how to do that. We tally up all the atoms, got 1 nitrogen, 3 hydrogens. And the molar volume is 22.4 liters per mole. Okay. And so with that, we set up the following relationship, and we end up with 0.761 grams per liter. And you might ask, well, wait a minute, how's that happen? Well, let's just take a look at the units. Okay. Well, let me restate that. If you were to do mathematically, if I were to take 1/2 and divide that by 1/3, oh, let me do it over here. 1/2 and divide that by 1/3. You know, we're dividing by a fraction. Don't we simply take the fraction in the denominator and invert it? So it becomes 1/2 and then invert the 1/3 to 3/1, right? And we end up with 3/2, right? Okay, well, we do the same thing here with respect to the units. Because the units here, we got grams per mole divided by liters per mole, okay, which is our fraction there in the denominator. Invert that, so we end up with grams per mole times moles per liter. And guess what? The moles cancel, leaving you with units of grams per liter. Okay, so that's why we're able to do that. But again, only for a gas and only for being at STP, standard temperature and pressure. Now, before when we were calculating the molar mass, we were tallying up the number of atoms in the count, okay? Figure out the molar mass. Okay, now we're going to take that and go one step further, because with that information, we can now determine the percent composition of every atom within the formula. So, for example, let's take water. And earlier, I demonstrated that the molar mass of water was 18.02 grams per mole, right? Because they had 1 oxygen, 2 hydrogens. Okay. Well, if we take each individual atom, so we start with hydrogen. Hydrogen brought to the table 2.02 grams per mole, okay? And divide by the total molar mass, okay? And we multiply that by 100. Guess what? We get a percentage of hydrogen. So in water, hydrogen makes up 11.2% of the whole molecule of water. If we do the same thing for oxygen, you know, there's only 1 oxygen, 16 divided by the total molar mass times 100, and that consists of 88.79% oxygen, okay? And these percentages should tally up to be 100%. Okay? Now that percentage is true for a formula of H2O. And whether you analyze H2O here on Earth or here in New Mexico, if you will, or in China, it's still going to be 11.2% hydrogen and 88.8% oxygen, okay? Or if you found some water out any place. As chemists, we utilize this to help us determine the structure of the compounds we synthesize and make. Because once we make a new compound, we send it off to do analysis, it comes back to us for whatever percentage of carbon, hydrogen, whatever we want, oxygen, sulfur. Okay, and knowing what we put into the reaction, knowing what the other instruments tell us, we have a pretty good idea what the structure is, and then this percentage composition just verifies what we came up with. Doesn't tell us 100% that's what it is. We got other things combined with this to tell us that, yeah, this is the compound you make. All right, so that's the percent composition, pretty straightforward, I hope, you know. It's simply the contribution of each individual element divided by the molar mass times 100. And it should all add up to be 100%. If it doesn't, then check your math, something went amok. Okay. So, for example, here's an example. If here we try to find the composition for TNT. Okay. If anybody know what TNT is, or what it can do?
It explodes.
Yes, it does. It's dynamite. Okay. Its chemical name is trinitrotoluene. It was, anybody by chance know who's the gentleman scientist that created this? I'll give you a hint if you don't know. But there is a yearly prize given out to people like in medicine, chemistry, and physics, peace, named after him, Nobel. Yep. And so he's the one who created this, and obviously it made him a ton of money. So here you're given the general formula: 7 carbons, 5 hydrogens, 3 nitrogens, and 6 oxygens. So we tally all those up, okay? And we run it through, when we do the atomic weights, remember to utilize our periodic table, okay? Because again, the answers in Canvas are based on our periodic table. Some periodic tables, they run the decimal points up to, 4 or 5 decimal places, and that can mess up with your answer. All right, so 7 carbons each at 12.01, that's 84.07 grams per mole. We have 5 hydrogens each at 101, okay? And then we have 3 nitrogens at 1401. And then we have 6 oxygens at 16 apiece. So that gives you a tally of total molar mass for TNT of 227.15 grams per mole, okay? Again, to put this in perspective, if you weigh out 227.15 grams of TNT, you have 1 mole, or 6.02 times 10 to the 23rd molecules. Okay. Now, once we got this information, go through each one individually and divide it by the molar mass. There's a carbon times 100, and that's what, 37.01%. The hydrogen is 2.22%. Nitrogen's at 18.5%, and oxygen's at 42.26%. And that should tally up to 100. So that is the percent composition for trinitrotoluene, which is a very difficult compound to make. When you nitrate toluene, there's 3 what are called nitro groups. 2 of them are fairly okay to, no too much of a problem to put on, but that 3rd one can be very challenging, very unstable. Okay, so be able to do the percent composition of any compound that's thrown at you, okay? You don't need to know what it is. If you're given the formula, you should be able to figure out the percent composition of all that, okay? So try these at home. You should get, for example, how many liters is 3.4525 grams of carbon dioxide gas occupy at STP? You should end up with calculate at 1.74 liters, okay? How many molecules are 3.425 grams of carbon dioxide? You should end up with an answer of 4.68 times 10 to the really 22 molecules. And then how many grams is 3.0 times 10 to the 15 molecules of carbon dioxide? You should have 2.2 times 10 to the -7 grams, okay? So try those at home. These are very similar to what we just went over. If you are having problems with the challenges, let me know and send me an email and we will, I will get back to you as soon as you need, okay? 1 second. All right. That, ladies and gentlemen, to get you ready for chapter 12. All right. Any questions? Any questions? There are a couple of questions that were brought up, and but before I begin those, let me read. Is any questions in general? Okay. The questions I was asked was, I'll put them up here. It has to do with the balance. And then one was what was being oxidized and what was being reduced. I'll go over these, not a problem. And then if there are not any questions, oh my goodness, because I just got a note that my battery's running low. So let me quickly run over these questions. Okay, and I'm glad I got chapter 12 done. All right, let me do this. Let me see if I can, let me share this. I have to work quick. Okay, I hope everybody can see this. Okay. Okay, first question was need to balance it. Okay. And so we have silver nitrate in the presence of copper 2 chloride reacting to give us silver chloride plus copper nitrate. Okay. Well, if we look at this reaction here, it is a double displacement reaction because silver chloride is solid. Copper chloride, silver nitrate, all soluble. Silver chloride is insoluble, and nitrates are always soluble. So this is an example of a double replacement reaction. Right, we need to balance this. So if you look at over here on this side, let me change the color a little bit. It's not showing it very well. I have 2 chlorides over here. Okay. And I have 2 nitrates over here. So try one or the other. Let's balance the nitrates. I got 2 nitrates on the right side. So what happens if I put a 2 nitrates right here? That would balance my nitrates, right? Okay. Now, in doing that, it kicks up my silver. Now I got 2 silvers. So what I need to do